Hello my friends, and here we go. Are you ready to implement that final training loop? I'm super ready and I'm super excited. Here we go. So we're going to start of course with for, then according to you what is going to be the loop variable? Well, that's of course going to be the episode. So let's call it episode, and our episodes are going to go in the range from the first episode of index 1 up to the number of episodes variable. But remember, the upper bound of a range in Python is excluded, so we have to add here a +1. All right, and here we go. Now let's implement that for loop. All right, so now according to you, what is going to be our first step? Well, as always in a training loop, especially in reinforcement learning, the first step is to reset the environment to its initial state at the beginning of every episode. And right now, since we're dealing with one episode specifically, starting with the first episode, well, we have to reset the environment to its initial state. So how we're going to do this? Well, we're going to take our state, which here is a new local variable, and then add a comma followed by an underscore, because then we will call, of course, our environment and then the reset function. And actually this returns not only the initial state but also some other information, like for example the initial observation, which is discarded here with this underscore. Okay, perfect. So then the next step, let me scroll down a bit, here we go. The next step will be to of course initialize the score, because the most important thing we'll have to measure here is the score. When I say the score, it's of course the cumulative reward, which is why we have to initialize this to 0. So let's do this. We're going to call that score, obviously, and we're going to initialize that to 0. All right, so this over the episode will be the cumulative reward. Perfect. Then we're going to start a new for loop now. And according to you, what will it be iterating over? Well, of course, I'm sure you guessed it. It's going to be a loop over the time steps, right? The time steps over the episode. Okay, so we're going to start this new for loop. Then let's call our time steps t, very simply. And then, well, these time steps are going to be in the range from 0, but we don't have to specify it. So let's just specify the upper bound, which is, of course, we initialized it before, the maximum number of time steps per episode. Right now that we called it like that, it seems super easy to understand, right? So let's paste it here, and that's our second for loop. So here we go. Let's implement it. According to you, what is the first thing we should do in this second for loop? Well, actually the question should be, what is the first thing that the agent should do at a specific time step? You know, at the beginning of this new for loop, looping over the time steps. Well, of course, it will be to select an action, okay? And so we're going to introduce a new local variable, which will be the action selected. And how will the agent select that action? Well, of course, that's with one of the tools we implemented before. First, we're going to call our agent, which we just created before, as an instance of our agent class. And then, well, speaking of the agent class, we can now use one of its tools, which will be, of course, here, the act method. The act method, which, remember, selects an action in a given state of the environment and following an epsilon greedy policy. Okay? So, speaking of state and epsilon greedy, well, what are the arguments here? Of course, the state, so let's implement it now. That's of course the state here we got in the first step, and then of course it's going to be epsilon. Okay, great. So now we have the action. So now according to you, now that we have the action, what is the natural next step? Well, since we have the action, what does it mean? That means that the AI just played an action, it just made a move, and therefore by making this move it ends up in a new state of the environment, and therefore because it played this action, we now have the next state. And of course, what do we also have? Well, we have the reward. Because each time the AI plays an action, it receives a certain reward, which, by the way, my apologies, I forgot to show to you in details. Let's have a look at what exactly this reward is. So I'm going back to the lunar lander environment, scrolling down to the description here. And so let's just see quickly how the rewards work. Well, after every step, a reward is granted, of course, but then this is what we're interested in. Here is the reward for each step, meaning for each time step now in our for loop. Well, the reward is increased, decreased, the closer or further the lander is to the landing pad. Okay, makes sense. Then it is increased, decreased, the slower, faster the lander is moving. Okay. It is decreased the more the lander is tilted, angled, not horizontal. It is increased by 10 points for each leg that is in contact with the ground, decreased by 0.03 points each frame a side engine is firing, and decreased by 0.3 points each frame the main engine is firing. And then finally we have the worst punishment and the ultimate reward. We have an additional reward of minus 100 points if the AI crashes, of course, and plus 100 points if it lands safely. And I can assure you that we will get those plus 100 points. Alright, so let's go back to our implementation. It was good to understand how the rewards work. And now, well, since we played this action and therefore reached the next state and got the reward, well, we're going to put those new information in new variables. So here we go, next state, then reward, and then also we'll also have done. The boolean saying whether we are done or not with that specific episode of the environment. And actually now, since we're about to use the step function from our environment, this will also return some other information but which we won't need, so we will just discard this information with a first underscore here and another one. Alright, and so all this will be returned by the step function of the environment, so I'm calling the environment first, and then this step function will take as argument, of course, the action. Okay? Great. And now, finally, time for the most important step of this training loop. Now is the time we're going to use the step method that, remember, includes the learn method. In other words, we're going to use the tool that will perform the training. Indeed, we have everything we need to call this step method, right? We implemented it in the agent class. Remember this step method. It needs the state, the action, the reward, the next state, and done. And well, this is exactly what we just gathered. And remember, the step method includes the learn method, which of course performs the training by backpropagating the loss between the expected Q values and the target Q values with our optimizer here and on the sampled experiences. So let's do this. That's the most important step of this training loop. Here we go. Let's use the step method to perform that new step of the training. All right, so how we're going to do that? We're going to, of course, take our agent from which we're going to call the step method. And there we go. We're just going to enter its inputs that we just gathered, the state first, then the action, then the reward, then the next state, and finally done. And that's it. This step is exactly what will train our agent to land better and better on the moon. Okay, perfect. So then what is going to be the next step? Well, now that we've reached the next state, we need to update our state variable because it becomes the next state. So we're going to do that simply with a state equals next state. There we go. Then we're going to have to update the score, of course, because we got the new reward. So since the score is the cumulative reward, well, we just need to increment the score with that new reward. Perfect. And then finally, we took care of the action, we took care of the next state, we took care of the state, and we took care of the score. What is missing now? We need to take care of this. Done. And how we're going to do that? We're just going to check if at this specific time step where we are in the second for loop, well, our episode is done. And so if done, meaning if the episode is done at this specific time step, well, we'll simply do a break so that we can finish the episode. Okay, great. And so, well, if the episode is not done, we will continue this second for loop. And if it is done, well, we will, of course, exit this second for loop. And so then what happens now? You know, when the episode is finished, well, we're going to append the score of that finished episode to that window of the scores on 100 episodes. And so, well, we're just going to take our variable here. We're going to copy it. And outside of the second for loop, be careful. We're going to paste it and then add a dot and append, of course, the score of that last episode that was just finished. Perfect. And then finally, we're just going to, of course, decay the epsilon for the epsilon greedy policy while ensuring that it doesn't go below the ending value of 0.01. And so how can we do this efficiently? Well, we're going to take our epsilon and we're going to update it this way by taking the max of first the epsilon ending value and then of course the decayed epsilon, which is epsilon decay value times epsilon. And my friends, now huge congratulations because we are done with that training for loop. So now I can't wait to see you in the next tutorial where we're going to do a one final print in that same for loop to visualize the training results. It's going to be a fun and exciting tutorial. I can't wait to meet you there, and until then, enjoy AI. Hello my friends, and here we are at the end of this training implementation. We just have to do one final print to print the training result, and we're not going to make a classic print, we're going to make a very exciting one because we're going to make a dynamic print, meaning that we will get the average score for each episode, but in a dynamic way, meaning that episode by episode we will see the average of the cumulative reward evolving over the episode, but we're going to make an overwriting effect, meaning that each of these lines printed will be removed to give place to the next one. And of course, we will keep the average reward over 100 episodes every 100 episodes. Okay, so it's a bit of an advanced print, but you won't be disappointed at the end by the result. Alright, so here we go. First, we're going to make that first dynamic print, which will print those average scores for each episode with that overriding effect from one episode to the next. Alright, so here we go. We start with print. Then we're going to start with some quotes because we're going to use the format function. So, first in the quote you enter the string, and then outside of this quote you're going to add dot format, which will contain the variables corresponding to the values that we're going to enter inside these quotes. Okay, so that we know that's a usual technique of printing. So first let's enter the print, and then I'll show you how to make that dynamic overriding effect. Alright, so we're going to start by printing episode, the episode number. So that is just the string, and then to add the number, we're going to add a space and then this pair of brackets, like that. Then we're going to add this \t, which is a tab character just to add some space. And then we're going to add average score, which will be, of course, the average score, meaning the average cumulative reward over the last 100 episodes up to this one, unless we still haven't reached 100 episodes, in which case it would be from 0 to this one. So then we're going to add in another pair of brackets like that. This time, since it's going to be a float, and since we have to choose the number of decimals we want to have up to the comma, we're going to enter this colon dot 2f, meaning that we will want the average score to be printed as a float with 2 decimals after the comma. Alright? And here we didn't have to enter anything because it's just an integer, which is the number of the episode. Okay? So all good with this, and then inside the format function now, we will have to enter 2 variables. The first one that will give us the value of this episode, and the second one that will give us the value of this average score in this particular format. Alright, so let's start with the first variable, the obvious one. The variable that will give us the number of the episode is, of course, our episode loop variable. And so that's the first variable we enter here. Okay, good, that was the easy one. And now the more difficult one, how we're going to get the average score in a variable here. Well, unfortunately, we don't directly have it, so we'll have to compute it. But what we have is this, scores on 100 episodes. And so according to you, how do we get that average score thanks to this scores on 100 episodes? Well, by using, of course, the mean function by the NumPy library. So that's why here I'm calling the NumPy library, from which I'm calling the mean function, which will take as input, of course, our scores on 100 episodes variable. Alright, so note that as long as we haven't reached 100 episodes, actually the scores on 100 episodes variable will contain less than 100 episodes, and therefore we'll get the mean of less than 100 episodes, but at the end, of course, we will get to 100 episodes. Okay? And now, finally, let's create that dynamic effect with the overriding effect. So the trick to do this is simply to add at the very beginning here, inside the quote, a \r, which is called a carriage return in programming, meaning that the cursor will return to the start of the line when printing. And so when you use it in a loop, well, it will allow the newly printed line to overwrite the previous one, which is exactly the effect we want to create. You will see it's going to look very, very nice. We'll have a dynamic effect in the console. But then that's not all. We also need to add at the very end, but inside the parenthesis of the print function, of course, a final argument, which is the end argument, and which we will have to set equal to a pair of quotes. Okay, just like that. And that means that after printing this line, it won't automatically add a new line. And this is crucial to create that overriding effect caused by this carriage return \r. Alright? So great, we have the dynamic printing, but then remember that we also want to keep the average score on 100 episodes every 100 episodes, and therefore we're gonna naturally make a new if condition here that will check whether we are every 100 episodes. Okay? And so how we're gonna do that? Well, you know the trick. We're going to use modulo again, you know, that percentage giving us the rest of a Euclidean division of an integer by another. And what will be that integer? Well, that's of course going to be the episode, because we're going to check if the rest of the Euclidean division of the episode by 100 is equal to 0. All right? Because if yes, if that rest is 0, then that means that we are every 100 episode. If episode is 100, then the rest of this is 0. If episode is 200, then the rest of this is 0 as well, because 200 equals 2 times 100 plus 0. All right? And so, if we are every 100 episodes, what are we going to do? Well, we're going to do this exact same print, but without that dynamic overriding effect. And therefore, right here, I'm going to paste that same print, and then we're going to remove at the end this end argument. We just remove it, and so then this print will stay. Perfect. And now, according to you, what else do we have to do? We have to do one final thing that is very important. I'll give you a hint. It has to do with the way the Lunar Lander environment works. Let's have another look at it in Lunar Lander Gymnasium. Let's have a look again at the rewards. If you remember, there you go, an episode is considered a solution if it scores at least 200 points. And therefore we need to check that, because if this happens, that means we win. And so we have to say this in the print and also save the model if we win, because it would be nice to keep a winning model. That works very well. And so, back into the implementation, we're going to create below a new if condition, which this time will check if, well, the mean of our scores on Google Colab will find it. There we go. If the mean of our scores on 100 episodes is larger than 200, and we have to add 0.0 to make it a float, well, if the average score in 100 episodes is larger than 200, well, time to say we win. And so, let's paste the previous print again, and let's change this the right way. So first we're gonna replace this by a /n to jump a new line, and then say environment solved in, and then in brackets we're gonna enter colon D because it's gonna be a double integer. So environment solved in a certain number of episodes. So I'm going to add here episodes. Then we're good for the average score, that's fine. However, in the format function, here, do you think we have to keep episode or change it a bit? Well, actually, if this average of the scores on 100 episodes is larger than 200, that means that in fact we actually started winning from this episode number minus 100, because this is a score over 100 episodes. So here, as you want, you could either keep just episode or subtract 100. That's up to you, okay? Let me actually zoom out a bit so that you can see better the whole code. Another one. I hope it's not too small for you. Let me know in the comment if you can still see well. I can always re-record this. Okay, then we will also remove this AND argument at the end because we don't need the dynamic overriding effect. And now we're good. And so, now what are we going to do? Well, since we have an intelligent AI that is able to land on the moon, well, time to save its model parameters. And how do we do that in PyTorch? Well, first, we call the torch library, from which we call the save function, which will take as input two arguments. Well, first, the model parameters that we want to save, and then second, a file in which we want those model parameters to be saved. So let's enter the first argument. How do we get those model parameters? Well, first we have to call our agent. Then from our agent, we're going to call our local QNetwork. There it is. And then from a local QNetwork, we're going to call a method that will return to us in a dictionary those model parameters, and that method is state underscore dict parenthesis. Okay, perfect. And then the other argument, the file that will contain those model parameters. And well, we simply have to enter a name of that file, so we can call this checkpoint.pth. Okay, perfect. And then now we have one final step, meaning one final line of code we need to do in this training for loop. According to you, what is it going to be? Well, now that we solved the environment, now that we have an AI working properly to land on the moon, well, it is time to exit the training loop, right? Because we don't need to do more training. And how we're going to exit this training? Well, with a simple break. And that's it, my friends. We are now ready to run this training for loop and observe some very exciting training results. All right, so are you ready? Let's do this. Let's do this now. But first, it's possible that because we implemented a lot of code, your session actually expired. So if that's the case, what you only have to do is click runtime here and then restart runtime. Okay, don't do restart and run all because we still have the results visualization, which I want to show you in the next tutorial. But at least restart the runtime and then rerun the different code cells we implemented together one by one until reaching this one. Okay, and once it's done, well, now is the time to run this last cell we did. So here we go. I'm going to do it in 3, 2, 1, go. And here we go. Now the training is launched. And you can see the dynamic printing of the episode with the average score. And as you can see, at first we start with some negative average scores, which is completely normal. You know, we just need to give some time to the AI to explore, to do some exploration, to train, to learn, and to update its model parameters, to update its Q values. Basically, it will take a bit of time before we see a better score. But as you can see now, we already increased the average score. You can see it increase a bit over time with this dynamic printing. So yeah, there we go. We started at minus 146. Now we're at minus 104, which is pretty good. And now there you go. We're over minus 100, minus 95 for the 200 episodes. And now minus 91, minus 89, minus 86. So you see, it is improving over time. It is amazing. The deep Q learning model works very, very well for this environment. And it keeps increasing over time, over the episodes. Now we are at episode 230 and the average score keeps increasing. And soon we will have a positive average score and mostly an average score over 200. So yeah, let's just continue watching and very, very soon we will see some positive average score. I can't wait to finally discover the score. Now we are at episode 263 and we have reached an average score almost close to minus 50. So as you can see, it is still exploring a bit. It is still doing a bit of exploration. It is still learning thanks to not only the deep Q learning model we implemented, but also remember that epsilon greedy action selection strategy. And now there we go. We are over minus 50. We're at minus 45, minus 47. And we have reached almost the episode 300. We're approaching 300 now, and we have reached minus 47, which is completely normal. You know, it always takes time for the AI to learn, to update its model parameters in order to achieve the desired performance. But now we can see the average score kind of stagnating. It is still not increasing, but that's probably because, you know, sometimes it still needs to do a little bit more of exploration, and soon enough, well, it will improve. And there you go. Now we are over minus 40, minus 37. That's perfect. And we have reached episode 329. Minus 31 now. We're close to the 20s, the minus 20s. There we go. Minus 20s, minus 28, minus 27, minus 25. You see, it keeps increasing. Now it keeps improving. Oh, wow. It's going really well. Now minus 13. We're getting super close to the positive reward. Minus 10, minus 8, minus 6, minus 6. We have reached episode 349, minus 7. So still doing a bit more of exploration now maybe. Still learning, still updating its parameters, its model parameters, still updating the Q values. We're decreasing a bit, now minus 10, but then that's probably because of some more exploration. Minus 4 now, minus 2, and there we go. Congratulations, my friends. We have reached finally the positive average score. So it is really well improving. Plus 9 now, plus 11, plus 12, plus 13, plus 19. So you see how it is getting better and better over time, how it is really getting more performant, how it is learning better, how to land properly on the moon. And of course, in the next tutorial, we'll see the results in the video of that AI, you know, properly trained to land on the moon. We will see how it is able to train on the moon. But as you can see now, we have reached more than 400 episodes and the average score is still increasing. That is amazing. And so I'm very confident now that we will soon reach an average score of over 200. Now we are at 74, 76, and we have reached episode number 423 now. And we're still at 75, 78, still doing a bit more exploration, still updating its parameters, still updating Q values, still applying the epsilon greedy action selection policy while learning with deep Q learning. And the average score is now at 80. So it keeps improving, it keeps getting higher and higher. And we have reached episode 448, 449. The average score is still increasing. Now it is kind of increasing slowly, but don't worry. It will at some point, you know, increase more because sometimes it needs to do a bit more of exploration before, you know, really take a big leap in improvement and in performance. But there you go. Now we are approaching an average score of 100 and we are approaching the episode 500. And remember, the total number of episodes over which we want to do this training is 2000. So we still have some time, we still have some good margin before reaching that objective, that goal of 200 average score. So now we are at 96, we're approaching the 100, and there we go, 100, perfect. So we're getting close, we're getting close. So average score 102, 104, 104 still. So we are now past the episode 500, good. So the average score is around 106, 107, 106 again. So yeah, it keeps improving, it keeps improving. Now it's probably doing some more exploration, on how to really take another big leap in improving the average score. But soon enough, we will see it at 110, and then 120, and then 130, and this will be exciting. There you go, 112, 113, 114, and the episode is at 546. By the way, feel free to share in the comments the average scores you get. Maybe you already won. Maybe you found an AI. Maybe you tweaked a bit the AI, the neural network architecture. I don't know. But maybe you already got the average score, the targeted average score of 200 before me. I'm at episode 569 and reaching an average score of 121. But maybe you got a better one before that. So feel free to share in the comment. Feel free to share your AIs, your architectures. And yeah, probably you will find an even better than the one we implemented together here. All right, so where are we now? We have almost reached episode 600 and the average score is at 128. So yeah, 132 now, 131, episode 600. So yeah, maybe we will get that final win, that final desired performance at episode 1000 maybe. It can change, it can vary with different experimentation. It's not deterministic at all, so let's see what we get. But now the average score is kind of stagnating. Oh no, it keeps increasing, very good. 134, 133, okay. So, very, very interesting. So, there we go, now we are at episode 650. And so, the average score seems to be still increasing. Sometimes we see it decrease, but that's completely normal. That's because sometimes the AI needs to do some more exploration to explore more actions that it can do in order to achieve the desired performance. But there you go. Now we are over 140 for the average score, and we have reached almost 700 episodes, and now over 150. So we're getting close. 153, 154, 154. We have reached more than 700 episodes now. So yeah, I think this is what I said. We're gonna finally win around 1000 episodes. So you see, we really don't need the 2000 episodes in order to achieve that final performance of the average score around 200. We are over 165 now. We're getting close. That's great. That's great. Maybe we will actually win before 1000 episodes. We could have actually, do this training over 1000 episodes only instead of 2000. But at least now we have some margin. We can feel confident that we will win before the end of the first for loop, looping over the episodes. Oh, wow. Now we are almost at 180 and sometimes decreasing a bit, but that's totally normal. That's because of the expiration. But there you go. 183, 84, 82. Oh, that's great. And we have reached 780 for the number of the episodes. So now it's stagnating around 180, but it's really increasing, it's really improving. So I feel totally confident that we will reach that targeted average score of 200 super soon. Now it decreased a bit, but that's again totally normal because of the expiration. It doesn't have to increase all the time. But there you go. I'm just betting if we're gonna reach that 200 average score before 1000 episodes or after. Let's take a bet. I bet that we might actually reach that average score after 100 because now it's doing some more exploration. The average score is decreasing a bit, but maybe at some point it will increase again because it will realize that the direction of the exploration it took is not the right one and it needs to go back to the previous subspace of the actions it took. All right. So 166 now after having reached 875 for the episode. And now it is increasing again. Good. 172, 173. So it found a new, better subspace of the action space, sub-action space. 180 again. Now we're back into the 180. Now 175. Okay. So 175 for episode 916. 174. 180 again. There we go. 182. Oh, maybe I will lose my bet. Actually, maybe we'll reach that 200 reward before 1000. 186. 188. Still increasing. Amazing. We have reached 945, 947, 190. There we go. First time we are over 190. 195, 96. I will lose my bet. We will actually win before 1000 episodes. There we go. Congratulations. We solved the episode in 863 episodes. with an average score of 201.64. Remember, the 863 is because of that minus 100. If you didn't use this minus 100, maybe you actually got 963. But that's an amazing result. Now I can't wait to visualize our AI landing on the moon in this part 3, which we won't re-implement because it doesn't really have to do with AI. It's more a visualization code, so we will just enjoy the results and see our spatially intelligent AI landing properly on the moon. I can't wait to meet you there. Congratulations again, and until then, enjoy AI. Hello my friends! Alright, so are you excited for this final tutorial where we visualize the results? Indeed, we're now completely done with the implementation. We don't have any more code to implement, related to the AI. So now is the time to just enjoy in our chair with a good coffee or a good tea the final results, visualizing our AI landing on the moon. Remember, between those two flags, and we should see a super beautiful landing because indeed in 963 or more, specifically 863 episodes, we were able to get an average score of over 200, which is the desired performance. Alright, so now let's get into part 3, visualizing the results. As I said, we won't re-implement all this because this is more a visualization code than an AI code. However, what's interesting to note is that, as you can see, first we get the environment, then we initialize the state, we initialize done to false, the frames, but then the important thing I wanted to show you is that in this while loop that will run an episode, well, as you can notice, we only use, of course, the act method for our AI to play the different actions in order to land properly on the moon, and of course the step method of the environment, to get the next state, the reward, and whether or not we are done with the episode. But what do you notice here? What do you not see that we had before when we implemented the training loop? I think that's very important to highlight this. Well, of course, we don't see the step method from our agent because now our AI is trained, so we don't want to do any more training. We just want to be in inference mode, playing the different actions to land on the moon. I'm talking, of course, about this step method that we call from our agent, and that, remember, includes the learn method in order to do the training. All right, and as you can see, we don't see it here in this visualization code. Alright, so we only use the step function from our environment to get to the next state until the episode is done, and then at the end we save all the frames in a video, which we will have, of course, and also in order to show the video in this Colab notebook, well, we use this show video function to show the video just below in the console. Alright, that's all you need to understand in this code. We don't have to re-implement it, so let's just enjoy, let's just watch our AI land on the moon. Are you ready for this? Here we go. So what we only have to do now, unless your session has stopped, in which case you need to restart it by clicking runtime here, and then this time you can do restart and run all. Well, mine is still on, so I can just run this cell and visualize the result. So are you ready to see a beautiful landing on the moon? Here we go, 3, 2, 1, go. Let's run the cell, and in a second we will have the video. Actually, not a second, but in a few seconds we'll have the video, and also here you will see, well, first you see the model's parameters saved in this checkpoint.pth file. So that's from the previous code cell that we run. But soon enough, we will see a video here, which we'll be able to download on our machine and watch anytime we want. But of course, we'll also have it here in the console. And indeed, it's going to take a little time, but not that much, because we're not in training mode, we're just in inference mode. So right now, our AI is just playing the different actions over one episode. It is not doing any training, it is not doing any deep Q-learning anymore. And since this code actually gathers all the frames together, well, it takes a little time to, gather these frames and include them into a video in the MP4 format. But the code is still running. All right. Oh, we are here, as you can see. The agent is still playing the actions. It is still returning the actions. And there we go, the code is executed after the agent played the actions. It was very fast to do the rest of this implementation. Are you ready to see the final video? Let's do this. 3, 2, 1, go. Here is our AI trying to land properly on the moon. It is very in control. It is playing some great actions. And look at this beautiful landing. That's a perfect landing. Oh my goodness. This is the first time I see such a perfect landing training this AI, because sometimes, it lands a bit on the right or, touching one of the flags. Here, it's really in between those two flags. That was a great one. So congratulations if you got the same thing. You probably got something very similar if you use the same architecture of the neural network. But there it is. That's a super beautiful landing. And as you can see, the video is also here if you want to download it. I'm gonna download this one to share it with you in the course. You just click on the 3 little dots and then download, and this will appear in our machine. All right, done. Let's have a look at it. Here it is. Here is the video. Let's watch it again in full screen, even if it will be lower resolution. But let's have a look one last time at this beautiful landing of our AI landing on the moon. Here we go. Super! So congratulations again. Now we're gonna do one final tutorial where we're gonna play a little bit with ChatGPT, trying to re-implement this with ChatGPT. Let's see if that's gonna work. I can't wait to do that final tutorial with you of this part 1. And until then, enjoy AI. Hello my friends, and welcome to the final tutorial of this module 1 on Deep Q-Learning. Congratulations for having reached so far by implementing together this Deep Q-Learning model. And speaking of which, now I want to say something very important, because in this tutorial we're going to build our Deep Q-Learning with ChatGPT. The really important thing that I want to say is that rest assured, all those 19 tutorials we just did together implementing ourselves Deep Q-Learning was completely worth it. It's very useful for you, because actually very few people can do it. Everybody can use ChatGPT to build a deep Q-learning model, but very few people can implement a deep Q-learning model as we just did. And therefore, that gives you a significant advantage as a data scientist or an AI engineer compared to people who are directly using ChatGPT to build an AI. Indeed, because we implemented the model together, you now know all the little details of the AI. You also know the foundations, the different layers of its mechanism, not only in terms of architecture, but also in terms of training. And therefore, that gives you so much more room for improvement compared to people who are directly asking ChatGPT to build an AI. So no worries at all. What we just did is extremely useful for you. It will make you one of the top AI scientists. But still, just for fun, let's build a deep Q-learning model with ChatGPT and see what we get. So let's start the chat. I'm going to say, hey, ChatGPT, can you please build a deep Q-learning model for the lunar landing environment? Okay, then I'm going to say, please implement it in PyTorch. By the way, PyTorch for deep reinforcement learning is undeniably much better than TensorFlow. Every expert will tell you that, even the experts working at Google. Today, this is a certainty. 3 years ago, I would have told you something different. But yes, today, PyTorch is the AI framework by excellence. All right. So please implement it in PyTorch, and please also include the code that generates the video of the trained agent at the end. Okay? Just like what we did, here we go. All right, so what do we have? Certainly. Below is a PyTorch implementation of a deep Q-learning model for the lunar lander environment from OpenAI's Gym. Yes, okay, so first it starts with the import, then it implements the DQN class, just like us. Okay, then it has a similar architecture to the one we use, but with different number of neurons in the fully connected layers. Then the forward function, of course, and then the DQN agent within a class. So we have the initialization of the parameter. It uses also an epsilon greedy strategy, okay? Then it initializes the Q network. Then, of course, it implements experience replay with that remember method. Then the act method, of course. Then replay, so that's for the experience replay again with the buffer memory. Then it updates the target model parameters with this update target model method. Then it initializes the environment, the state size, the action size again. You recognize the variables here. Then it creates the agent itself, and then it starts the training loop, looping over all the episodes and the time steps. And then it generates a video of the trained agent. And finally, we get that video. Okay, so at first sight, it seems pretty good, but I bet that whatever code you got, you probably got a similar code to this one. If you take this code and paste it in Google Colab, well, I'm pretty sure you will not get a performance training and mostly not that great results at the end, at least not as good as the ones we obtained, which is why I was telling you not only using ChatGPT for AI is easy, but besides, you will get much less great results than the ones we got thanks to the great understanding of AI we have while implementing our deep Q-learning model. But still, this is definitely some good work by ChatGPT. We definitely have a nice architecture here, a good class of the DQN agent integrating that epsilon greedy strategy as well as experience replay. Here is the epsilon greedy strategy. So yeah, that's not bad. And if you really want to be convinced that what we implemented is much better, well, I encourage you to try this code in a new Colab notebook, and you will see that the results will not be at that same level of quality we obtained while implementing on our Google Colab notebook our deep Q-learning model. All right, so there we go. I just wanted to finish this section with a little bit of code generation within ChatGPT and, play a little bit with ChatGPT to see the kind of implementation it would return. Now, I just want to say two things. First, huge congratulations again for having implemented your first advanced AI of this course, the Deep Q-learning model for the lunar landing environment. You did some great first work there. And now the second thing I want to say is that I really look forward to seeing you in the second part of this course to implement an even more advanced AI model, which is the Deep Convolutional Q-learning model, which is more advanced because indeed, instead of having a one-dimensional vector of input state, you will have multi-dimensional arrays representing images. Because this time, meaning for the environment we'll work on in this part 2, our AI will be playing a game with its own eyes, just like a human would play a game. And those eyes will be brought by the convolutional layers inside the neural network. It will be very exciting to implement. That's why I can't wait to see you there. And until then, enjoy AI.